So we have studied theorem on linear congruence, that a linear congruence Ax congruent to B modulo n has a solution if and only if D divides B, where D is GCD of A and n, and if it divides, then it has D incongruent solutions. If this condition is satisfied, then the D incongruent solutions are x naught. If one solution is known as x naught, the other solutions are x naught plus n by d, x naught plus 2n by d, and so on. The last is x naught plus d minus 1 times n divided by d. This is the theorem that we have proved last time. Now we write a corollary for this theorem, and that is, if GCD of A and n is equal to 1, then the congruence, linear congruence Ax congruent to B modulo n, has exactly one solution or unique solution. So, and this result directly follows from the theorem. See, what is D? GCD of A and n. If it is D, then D must divide B. And here it is 1. D, the value of D is 1. And 1 divides every integer. So, therefore 1 divides B. And it has only D number of solutions, means one solution. So, here we may consider D is equal to, D is GCD of A and n is equal to 1, and 1 divides B. Therefore, the congruence has only one solution. D number of solutions are there, and here D is 1, has only one solution. That is the meaning of this corollary. So, therefore, there are two cases, or we may consider there will be three cases. If D does not divide B, then there is no solution, and if D divides B, then there will be these two possibilities. If D is 1, there is only one solution, and D is other than 1, then there are exactly D incongruent solutions. Now we shall consider the problems from the book. Now it is the exercise 4.4. This is the problems set 4.4. Now see. So I shall write the problems here. Solve the following linear congruences. Say first, it is, now we will consider first as 36x is congruent to 8 modulo 102. So these are few congruences we shall solve now one by one. Now consider solution for one. Now we should compare this congruence. Given congruence is 36x congruent to 18 modulo 102. So here what is the value of A is 36. What is B is 18 and N is 102. Comparing with AX congruent to B modulo N. Now what we require is D. D is GCD of A and N. D is equal to GCD of A and N, that is 36 and 102. Now we have to find out the GCD of 36 and 102. We may use the Euclidean algorithm and find the GCD of these two, or any other way by inspection also we can find out. This is 36, so the quotient will be 2 and it is 72, and thus this is 30. We have to divide it by 36 by 30. Quotient is 1 and this is 6. We have to divide 30 by 6 and the process is complete. Last non-zero remainder is 6 and 6 is the GCD. So GCD of 36 and 102 is 6. Now we have to check whether this D divides B or not. Now what is B? B is here 18. See, we should say not 18 but it is 8. 36 is congruent to 8. We have to correct this. It is 8, not 18. 36 congruent to 8 modulo 100. Whether this 6 divides 8 or not. Now, but we know 6 does not divide 8. But this GCD, D does not divide B, since 6 does not divide 8, and thus this condition is not satisfied. D divides B, this condition is not satisfied for this congruence. And so what is what about the solution? So solution exists if and only if D divides B. If D does not divide B, the solution does not exist, and therefore here the solution does not exist, and therefore the solution does not exist for this congruence. So we have to stop here. The solution does not exist. And now we shall consider the second. So the possibility is solution may exist or may not exist depending on D divides B or D does not divide B. Consider the second, that solution for the second. 25x is congruent to 15. Modulo 29. What is value of A? 25. Value of B is 15. Value of N is 29. And what is the GCD of A and N? GCD of 25 and 29. Clearly it is 1, relatively prime. 25 and 29 are relatively prime, therefore the GCD is 1. And if the GCD is 1, 1 always divide any integer. So, and 1 divides 15, or from this corollary you see, the GCD is GCD of A and N is 1, then there is exactly one solution. So therefore, there is one solution. There is exactly one, or there is a unique solution. There is a unique solution. And find out that unique solution. Now how to find the solution of this 25 congruent to x, 25x congruent to 15 modulo 29. For that purpose, we can factorize this as 5 into 5, 5 into 3, and then 5 can be cancelled from both sides using theorem 3. So 1 implies 5 into 5x is congruent to 5 into 3 modulo 29. and we have to divide this by 5 can be cancelled, but we should note the GCD of this 5 and 29 is also equal to 1. So this modulo it to be divided by 1 means modulo remains the same, and thus this implies 5x congruent to this 5 cancels 3 under the same modulo 29, because we have to divide the by 1 29 by 1. So theorem 3. And now it is easier to solve this congruence than this one. So find out the value of x by inspection or by any other way is that we can consider this number 5. 5 is close to, which multiple of 5 is close to 29, that can be observed. And we know that 5 into 6 is 30. 30 is closer to 29, or actually 30 is congruent to 1 under modulo 29. So therefore we multiply this by 5, and thus this implies further not 5 but 6 to get 30. So this implies 30x is congruent to, multiply this by 6 on both sides, 18 modulo 29, multiplying by 6. Why multiplied by 6? Because now 30 directly reduces to 1 under modulo 29. So this implies we keep this number same, but this is x congruent to 18 modulo 29. Since 30 is congruent to 1 modulo 29, 29 divides 29, and therefore this is done. Or you may check the solution by taking the values of x as 1, 2, 3 up, and find by inspection. So 18 into 5, here also you may see 18 into 5 is 90, 90 minus 3 is 87, and 29 divides 87. So therefore this is a solution. This is a solution of the congruence. This is the required solution. X congruent to 18 modulo 9 is the solution for this congruence. You substitute this value of 18 and check here also. So that gives the solution for second problem. Now we shall consider the next. The next is 6x congruent to 15. Solution for 3. Now again, a is equal to 6, b is 15, n is 21. What is the GCD of a and n? GCD of a and n is GCD of 6 and 21, and that is clearly it is 3. So 3 and 3 divides 15, b. So this is d, d divides 15. And this is D. D is the GCD. So here D divides B. That is 6. That is 3 divides 6. Therefore, we may say D divides B, since 3 divides 6. D is 3, B is see, it is 15, not 6, but it is 15. 3 divides 15. So the condition is satisfied, and therefore this congruence, we may refer this as 1. Therefore the congruence by this condition, it has solution if D divides B. D is GCD of A and N. So therefore the congruence 1 has solution. 1 has. But how many solution? D incongruent solution. D means 3. The congruence 1 has 3 incongruent solutions. Incongruent solutions modulo, the module is 21. Now how to find the solutions further? Now again we see 1. Here we can divide this by 3. on both sides, and also we have to divide 21 by 3 because the GCD here is 3, not 1. So 1 implies, by theorem 3 we can say, you refer theorem 3. What is theorem 3 is CA congruent to CB modulo n, and if D is a GCD of C and N, then this implies A is congruent to B modulo N divided by D. That is theorem 3. And that means we can cancel this common factor, but we have to divide N by GCD of C and N. And you may observe what is the GCD of 6 and here, yes, it is 6 and 21, that is 3. So we have to divide this modulo by 3. By theorem 3, 1 implies after division by 3, it is 2x congruent to, divide this by 3, that is 5, and modulo, this will be modulo 21 by 3. Common factor is 3 here, that is cancelled, and 21 by 3 is again 7. So that is, this implies 2x is congruent to 5 modulo 7. Now we have to solve this. So this congruence is reduced in this form. Without reducing the congruence also, we can find the solution by inspection. So it is not necessary to write this congruence in this form. Directly you search for the solutions of this. But the numbers are smaller, then that will be easier to find the solution of this congruence. We have to find the value of x so that this congruence is satisfied. Now you see which value of x satisfies this. Try using the different values of x, that is starting with 0, 1, 2, 3, etc. But you see 2, 4 is not congruent to 5, 3, it is 6, and so on. That can be tried. But again, as in earlier problem, here the modulo is 7, and which multiple of 2 is close to 7, that we can say, and easily, or one number more to that 7, that is 8, and we see if you multiply this by 4, we get it 8x. Multiply both sides by 4, 8x, but 8 is congruent to 1 under modulo 7. So therefore that gives directly the solution. So this we multiply both sides by 4, that is 4 into 2x is congruent to 4 into 5 modulo 7, and this implies 8x congruent to 20 modulo 7. And now we may see this 8 is congruent to which number under modulo 7, that is 1 into x, and 20 is congruent to which number under modulo 7, positive. So 20 when divided by 7 gives the remainder 6. So therefore this is 6. 20 minus 6 is 14, and 7 divides 14 modulo 7. And thus one solution is obtained, x is equal to 6. You may check here, x is equal to 6, that is 12. 12 minus 5, that is 7, and 7 divides 7. So directly you can by observation also write x is equal to 6 is solution of this congruence, or if not, we may multiply by these numbers, and thus one solution. Thus x naught here is, x naught is equal to 6 is one solution. One solution of this congruence, that is last congruence we shall consider as 2. But the original congruence is modulo 21, and therefore we have to consider the modulo 21 solutions. But the congruence one is under modulo 21. And now therefore we have to consider this, the value of modulo as 21. Value of n is 21. n here is 21 and d here is 3, and write all the solutions. So therefore the how many solutions are there? 3 incongruent solutions. Therefore the 3 incongruent solutions, 3 incongruent solutions of 1, we can say. Solutions of congruent 1. Incongruent is important. 3 incongruent solutions. Theorem gives incongruent solutions. Are x naught are given by say x is equal to, we write in single equation, x congruent to x naught plus n by d times t, where t takes values under modulo 21, where t is having 3 values only, starting with 0. Here t is 0, t is 1, t is 2, and so on. So where t is 0, 1, 2, and thus therefore this x is congruent to x naught. Now we shall put the value of x naught. X naught is 6. What is n? N is 21 and d is 3. So 21 divided by 3 is 7. 7 times t modulo 21, t is equal to 0, 1, 2. And that is x is congruent to, put t is equal to 0, we will get 6, first solution. Put t is equal to 1, we get 6 plus 7, that is 13. Put t is equal to 2, we shall get 14 plus 6, that is 20, modulo 21. Are the solutions, are the 3 required incongruent solutions of first congruence or the given congruence, are the 3 required incongruent solutions, or are the required solutions. We have written about this, these are incongruent. Solutions of 1. So in this way we have to find out the number of solutions, whether we have to check whether the solution exists or not. If it exists, whether unique or many. And if d is 1, then unique solution. And if d is greater than 1, then d number of solutions. Here d was 3 and therefore we have obtained 3 solutions. And how we have written this? This is single equation. X congruent to x naught plus n by d into t. And why we have considered t values of t as 0, 1, 2? Because there are only 3 solutions. If there are 2 solutions, we have to consider 0 and 1. If there are 4 solutions, we have to consider 0, 1, 2, 3, etc. So these values of t depends on number of solutions, starting with 0, and that gives the required solutions, incongruent solutions. You may check putting these value in the original congruence. Now the remaining problems, you should refer the book and try to solve the remaining problems from the book. So thank you.